Okay, so here's a quick review. What we looked at day before yesterday, right? We looked at similar triangles, at some ways that we can prove triangles are similar, and the only kind of shortcut formula that we came up with was angle, right? And in this ought to remind you of, going back to like chapter 4-ish, when we had all our triangle congruence relationships. Remember, we had SSS, we had SAS, ASA, and AAS, right? Those were all options for us, all ways that we could prove two triangles congruent. Well, for similarity, we're going to add some stuff like that. Yesterday, we added angle, and we're going to look at a couple other ways today. What did angle similarity say? If this is true, then the triangles are similar. So if what? Jacob, put that away, please. So what do we got here? Phones, all that stuff should be away. If what is true, then we know by angle the triangles are similar. This was a pretty simple one. What did it say? What's the AA stand for? Yeah, two angles, right? So if two angles of one triangle are what? Say it again. Congruent to, right? Two angles in another triangle, we know that they're similar, right? And the reason we knew that, remember, was because if two of the three triangles are congruent, triangles all add up to 180, so the third angles must also be congruent. And if all the angles are in any figure are congruent to all the angles in another figure, then they have to just be scale versions of each other, so they have to be similar, right? So that's what we had earlier in the week. Let's just extend this just a little bit. Okay, so we get two of them. We get side similarity, so SSS, not congruence, but SSS similarity, and side similarity, SAS similarity. Here's what they look like. Side similarity just says, and you've already done some stuff with this, honestly, without knowing it. Side similarity just says if all three corresponding sides of two triangles are proportional, then you know the triangles are similar. Without knowing anything about the angles, you don't need to. You know that the triangles are similar. So in this case, for example, if we've got this big triangle ABC and this little triangle PQR, if we look at corresponding sides, if the ratio of AB over PQ, so we're doing, our scale factor is small to big or big to small? Big to small. Okay, so good. We got large to small. AB over PQ, if that's in the same ratio as BC over QR, and that's also in the same ratio as CA over RP, so if all the color coordinated sides are proportional to each other, then guaranteed the triangles are similar. Okay? So that's one of them we get. And the other one we get is side similarity. And what this one says, same kind of a thing, only instead of three sides, if we just have two pairs of proportional sides, corresponding sides that are proportional, and the included angle, the angle between the two, it has to be the included angle. So for example, if we look at these two triangles, we get the big triangle XYZ, the small triangle MNP, and if angle X is congruent to angle M, as it's shown, then the including sides, so the sides next to those angles, have to be the ones that are proportional. So for example, our ratio of, it looks like large to small, I would have to have ZX being the ratio of ZX to PM, so that ratio would have to equal the ratio of what do they call this? XY to MN. So big pink to small pink would have to equal big green to small green, and the included angles would have to be congruent to use SAS. Okay? All right, so let's quickly look at an example or two of that. That's it. So real quick here, let's try these three triangles out. Let's decide which of the three triangles are similar. Do we have any information about angles there in those three triangles? What do we got? Any angle information? See any numbers in the angles? No, we got no information at all about the angles. We can't show that any pairs of angles are congruent. So what's the only way that we could, if we're going to show that these triangles are similar, then what's the only way we have? Yeah, SSS. We have to use the sides. So we would just test it out and see, right? If we look, let's compare, let's say the first two. So this triangle and this triangle. Well, if I compare the ratios of the red side, so I guess I'm going to do a scale factor that is large to small. So 6/4 would have to equal, which reduces to 3/2, right? Would have to also equal the ratio of, what are we doing next? 12/8, because those are corresponding sides. Well, that also reduces to 3/2, right? So far, so good. Olivia, you turn around, please. Amanda, what do you got back there? Take a look at this. Put that away for a second. You'll have time. And then last one, we'd have to have the ratio of, you can't see those very well, but that's 9/6, right? If we look at these kind of, whatever that is, lime green to lime green, big to small would be 9/6. That's also 3/2. So because all those ratios of the corresponding sides were the same, they're all proportional. And so they definitely are similar, right? The first two triangles are similar. Okay, well, let's try out another pair. Okay, let's look at, I guess, the first and the third. Did I miss that? No, yeah, the first and the third. Okay, yeah. So if we compare, let's say, the red sides. So this time we're going, let's see, I guess it's hard to say. I guess this is small and that's big. So we get the ratio of this red segment, AB, to this red segment, GH, is 6/6, so that ratio is 1, right? If I look at the ratio of the blue sides, the blue side in this triangle has a length of 12, and this triangle it has a length of 14, so we already know it's not going to work, right? Because that ratio is 6/7, and that's different from 1, so I wouldn't even have to do the third one. It makes no difference, right? I know already that all three pairs of those sides are not proportional. So the first triangle and the third triangles are not similar. Do you suppose it's possible that the second triangle and the third triangle could be similar? You're right. Yeah, it wouldn't work, would it? If I know that the first and the second are just scale versions of each other. I took the first one and I just shrunk it all down proportionally to get this one, right? But the first and the third are not scale versions of each other. Then there's no way that the second and the third can either, right? Because these two are, right? They share, 1 and 2 share the same ratios. So if 1's ratios are different than 3's, then 2's can't be the same either, right? So the only pair of similar triangles would be the first and the second. All right, so what about this one then? You're going to be doing some stuff like this. Using side angle side similarity, let's prove that the big triangle RST is similar to the small triangle PSQ. Okay, so to do that, just let me see what that's left with. Okay. So what can we do? Little triangle and big triangle. If I'm going to use side angle side, where do you suppose we want to start with that? Well, maybe I could, but remember I have to use the two sides I need to use are the two that surround the included angle. And I don't have information about all three sides, do I? I only have information about 2 of the 3 sides of each triangle. Okay, so I mean, it's not that much of a big deal about this, but what's going to be the angle that's going to be congruent in both of those two, and why? S. And how come? This goes back a ways. How come S is the congruent angle in both of these two triangles? How come? It's a shared angle. Sure, it's a shared angle, so it's the same angle. So angle S is congruent to itself. Do you remember the reason for that? Why is something congruent to itself? What property is that? Remember? Reflexive property, yeah. So angle S is congruent to itself by the reflexive property. Now, we're not going to go into these long proofs, but there's the angle, so let's draw that in. Now we just got to get the ratios of the sides, right? So we've got, it looks like if that's the included angle, I've got on the left, I've got this short side and then this long side. And I have to show that the ratio of the blue sides is the same as the ratio of the red sides. There's the short side and there's the long side, right? And that's easy enough to do. I'm going to get rid of those. You can't see the numbers. But it looks like if I go small to big, aren't I making the ratio of this side is going to be 4? What's the length of the whole side of this, the whole vertical left side of the big triangle? 16? Okay, so we're going to get, okay, so we're going to get, I guess big to small would then be 16 to 4, right? Would have to equal what ratio on the other side? What's going to be the big to small ratio of the right side of those triangles? What's the big length? ST. What's that overall length going to be? 20? Okay. So I'm going to have big to small would be 16 to 4 would have to equal 20 to 5, and that works, doesn't it? In both cases, I just get the ratio. I probably should write it this way: 4 over 1, right, or 4 to 1. And so it works. The included angle is congruent. The two pairs of the corresponding sides next to the angle are proportional. So by SAS similarity, we got it. We just proved it. Last one. So what about this then? Let's say, this is kind of hard to see what's going on here, but this is like a survey problem. So we want to find the width of this river. So here's the river. It's flowing along like so. Here's one bank of the river. Here's the other bank of the river over here. There's the water flowing down the river. Okay, we want to try to estimate the width of this river by just using some geometry. So there's a way we could do this. We could set up over on one side of the river, we could measure out this little right triangle. Okay, so let's say it's going to be, what are we talking here, feet probably, or I guess we're talking feet. So it's going to be 12 feet. This side of the triangle is going to have a length of 12 feet. This side's going to have a length of 9 feet. We'll make sure it's at a right angle. Then all we have to do is we have to just sight along this side. So from that point to that point, if I just look in a line along those 2 points, I got to see where that line hits the other side of the river. It's that point right there. I got to sight right along these 2 points, and wherever that line of sight hits the other side of the river, we'll make a mark there too. All we got to do is have somebody on the other side of the river just measure this distance along the river, and if that's 63 feet, and I know these dimensions, you see how we can get this width. First of all, are those two triangles similar? This triangle and the big triangle, it spans the river, and this little triangle on one side, the little survey triangle. By what? Why are they similar? What's the reason? Two angles are the same. They both share a right angle. Okay, good. So there's an angle, and then they both share this. These are vertical angles, aren't they? So they also both share that angle. So we know by angle they're similar. All we got to do is just set up a little proportion, and we got it. Okay, so we know, I don't know where the letters went. But we could just say something like big over small equals big over small. Let's just color code this instead. So we've got, how about big red over small red would have to equal big green, oops, that's not green, have to equal big green over small green, right? And there's our ratio. So there's the ratio of the reds. The ratio of the greens is right here, but instead of calling that RQ, let's just call it X. How about? So X over 12 equals 63 over 9. That's easy to solve. Just cross multiply. Actually, just multiply both sides by 12. And I end up getting an answer of 12 times 63 divided by 9 is 84. 63 over 9 just reduces to 7, doesn't it? So that's just 7 over 1. Cross multiply. So we got it. 84 feet across the river. People do that in surveying. You do that all the time. That's how you survey. It's just geometry. You ever see the guys when they're working on roads and they've got those little tripods set up with the looks like little telescopes? Those are surveyors, and they're just looking. They can look through that thing and they can see the line of sight. A little laser in there, so they can just mark where the laser hits on the other side. That's the kind of stuff they're doing. All right, I think that's good. How about that? Was quick. Was that not quick?